But before we start the lecture, I wanted to point out a correction that you need to make on the homework assignment. Okay, so one of your classmates noticed a problem with the graphing for the second problem. So problem 2 on the handout I gave you, if you turn over to the back page, here on the second bullet point of the back page, it says plot such that the x-axis is bounded from 8 to 24, and that's fine. And then it says, and the y-axis is bounded from 0 to 35. So if you have that be your y values, then you're not going to see anything, because if you look at the data that's provided, the intensity is from 950 down to 140. So that domain for graphing wouldn't give you the view that you need. So where it says 0 to 35, change it to say from 100 to 1,000. And then once you change it from 100 to 1,000, I think that within that range, you'll be able to see the data that that's provided. All right. So any questions about that? Not 0 to 35. Let's do 100 to 1,000. All right. I'll also remind you that these lectures are recorded, and so I was looking over the homework before class, and I think probably problems 1 and 2 are fairly straightforward. It's the third problem that may be a little bit further back in your memory, because it's asking to use the polyfit and the polyval function. And so, we covered that last week. Before that, Thursday didn't meet in class. And so if it's not fresh in your mind, I'd suggest you could go back to the lecture recording and work through those sections again to refresh your memory on how polyfit and polyval functions operate. And I think between that and then the suggestions that are on the assignment itself, hopefully that would get you headed in the right direction. All right, so what we're going to be doing today is now talking about two-dimensional arrays. Now, until now, our arrays that we've been using in Matlab have just been 1D, meaning that it would just be a single row if we were thinking about it in a tabular form. And so we're going to move on into two-dimensional arrays, which has more than a single row, so multiple rows. And then once we do that, we'll look at how, when you have 2D arrays, that affects the way that you do calculations with matrices and how you can solve equations, like systems of equations using matrix multiplication and so on. The assignment that we're talking about, this homework 8, is due on Tuesday, and so as per usual, just upload the assignment to MU Online before 11 a.m. on that day. And as it says on the handout, what you should be uploading would be 3 different M files. An M file for problem 1, a different one for problem 2, and a separate M file for problem 3. All right, so 2D arrays are a little bit different from what we've been doing with 1D arrays, and so we're going to discuss how to create them and how to do script programming with 2D arrays. So a 2D array, also sometimes informally called a matrix, is, you can see this one, we're saying X has 3 rows and 4 columns. And so if we were to create this in Matlab, it would be referred to as a variable. Variable X would be a 3 by 4. The characteristics that we'd see on the screen, there's the summary screen where it lists all of the variables you've created, and even before you double click on it and pull up the entire table that represents that variable, it still tells you how many rows and columns there are. So this is the 3 by 4 matrix. Let's create this matrix in Matlab. So if you haven't already, start the program. Mine started today without it even asking me to go through the licensing stuff, so that's progress. All right, let's create this array, and you'll notice that you can put in these commas to identify the separate numbers in each of the columns. The commas end up being optional. You don't have to put them there if you don't want. Sometimes it can help break it up visually, it's the semicolon that is the important must-have, because that's telling you to begin the next row. One thing I'll point out is that we would have an error if we didn't define 4 columns in each row. So you'll notice here's our first row, here's our second, and here's our third row. And each one of those 3 rows has to have 4 elements. If the first one has 4, then all the rest of them have to have 4. All right, so let's create that. Five, 35, 43, 7, 4, 76, 81, 8, 21, 32, 43. And you know, if you want to see it back, then you don't suppress the echo. If you're confident in your typing, then maybe it doesn't matter, but just to double check, it looks like I've keyed in all those values correctly. And then over here in the workspace, in the quick variable summary, it tells me this is a 3 by 4. So it means it has 3 rows and 4 columns. All right. So the commas that were shown on the previous slide are optional. I didn't bother putting them in when I was defining my matrix, so it can just be spaces if you prefer that. And if you have a really long matrix, then as you're typing it in, you can do an enter after each row instead of the semicolon. And so you can also do the same thing, not just when you're working on the command line, but when you're creating a script as well. You can just put in the, the hard return or an enter keystroke, and then that defines the next row in a matrix. All of the predefined functions that we've come to know and love before also can be used in the context of a matrix. And so here on the screen it's showing an example. If we were defining A as pi, then it's going to display pi rounded off to 4 decimal places there. We can put a function embedded inside of a matrix, and so the square root of 2, and it's going to be reporting the square root of 2, where 2 here is in terms of radians. Log of 7. So you can have functions built into defining a matrix. But as I mentioned before, you have to have the same number of columns for each row. So here, since in the first row we said there were 2 columns, there was column 1 and column 2, then that means once we start defining the next row with that semicolon, then there has to be 2 elements there as well. So there would be 2 columns for the second row. Otherwise we'll get an error saying that the matrix isn't correctly defined. Here are some interesting functions. Let's try these out. Try I of m. I don't know if, let's see here, where m is a number. So I of 3. So an identity matrix is one that has numbers along the diagonal. You may remember that from college algebra if you took it. And if we did I of 4, it's just going to be a 4 by 4 matrix where 1 goes along the primary diagonal there. Okay, you can try zeros, and what that's going to do is create a matrix full of zeros for as many rows and columns as we specify. So if we did zeros 4 by 2, then here we've got 4 rows and 2 columns of zeros. And if we wanted, we could assign that to a variable as well. So we could say q equals zeros 4 by 3. And so now it's created the variable q, and it has just zeros. And that can be useful if you want to create a variable and then go into the editor, double click on the variable and it brings up this variable editor, and then you could adjust the numbers as you need to. If most of the values were empty and you wanted to just manually edit a couple of them along the way, then that might be a viable way of approaching it. So now if we call on Q after having made those edits, you can see that the edits are repeated back. Anybody want to guess what ones is going to do? You saw what zeros did, so of course ones is going to do a similar thing. So ones will fill our matrix. If we wanted to have a 7 by 4 just full of ones, then you've got it. 7 rows, 4 columns of nothing but ones. And as before, we can assign that to a variable so that it's stored. And we can also use the same thing when we were doing a one-dimensional matrix and defining a string of variables using, for example, these colons, where we had 10 colon minus 1 colon 4. That was interpreted as start at 10, go through 4, and then at an increment spacing of -1, fill in the blanks in between. And so it goes 10, 9, 8, 7, 6. And so we're creating a matrix. In the first row, we have that kind of abbreviation for just do everything in between the two bounds at a given spacing. And then for the second row in this matrix, you can see we've given the command do a ones, where you've got 1 row and 7 columns. Now, it has to be 7. If it was 6 or if it was 8 or any other number, then this matrix B wouldn't be correctly created. So because the first row had 7 elements in it, the second one does as well. Okay, now the third row is just this sort of even spacing command again, 2, 4, 6, 8, and so on. And then for the final fourth row, you can see that we filled it in with a row of zeros. So let's try that out. If you haven't already, B equals 10 to, using -1 spacing, to 4. Okay, our next row is going to be full of ones, and it has to be 1 row with 7 columns. Then let's go from 2 to 14 with a spacing of 2. And of course, that's going to have 7 elements in it. And then we'll fill in the last row with zeros. And that will be a 1 by 7 full of zeros. All right? And since I didn't suppress the echo, it repeats back to me what B is once it creates that variable. All right. Now, I've already showed you that we can go into the editor and modify individual elements in a matrix. We can do the same thing from the command line, just like we did when we were working with one-dimensional arrays. You remember that we had command line instructions that we could go in, and once we'd created an array, we could overwrite individual values. So what we're going to be doing differently is that we're going to be calling the row number and then the column number to make those substitutions. So if you just want to find out what is the value in some matrix, you can ask it to call it out. So this command is saying, once you've created this matrix X, I don't remember, do we still have this in for X? Did we create that? We haven't overwritten that yet, have we? Let's see, what is X? All right, yes, this is our same X from before. So X is the entire matrix. But if we say X, I just want to know row 2, column 1, then it will report this 4. That is the individual element within matrix X. We can do X of row 3 column 4. So that's going to be row 3, column 4. It's going to be this space. Whatever is there happens to be assigned to 3. And of course, you could assign a new variable using this as well. If we wanted a new variable to be m, whatever's in that cell, we could say m equals x 3 of 4. And so now it's going to create a new variable m that has the answer of whatever was in that location. So that was just our row 3, column 4. But if we ask it to call on, so just to refresh our memory, here's x. If we say, tell me the 4th row and the 3rd column, there is no 4th row, so we get the error message there that it can't call out the data because it exceeds what exists in that matrix X. There isn't a 4th row. There's only a 3rd row. Any questions about how we call on the individual elements in a matrix? All right. We can use the colon operator to refer to an entire row or an entire column of information within a matrix. So here, this is our matrix X that we've been working with so far. Try asking it to give you 2, which means the 2nd row, and then the colon means all of the columns, so all of the data there. So if you do 2, comma, colon, that means row 2, all of the columns that we've got. So it'll just report as shown there. Or if you say, for X, I want to know all of the row, but the 3rd column, so here's our 3rd column, and all of the rows would be row 1, row 2, row 3, so 43, 81, 40. And that's what we'd get. Now this one's a little bit more confusing. Okay, so try and interpret this statement. 1 colon 2 and 2 colon 4. So remember the spacing here, the first piece of what's in the parentheses is the row information, and then the second piece is the column information. So what you're saying is you're saying, give me the information that is in both the first and second rows and columns 2 through 4. So whatever's in both of those have to be true. And so what it's not showing is it's not showing 5, 4, 21 because that is in the first column, and this is saying only show columns 2 through 4. And it's also not showing 32, 40, and 3 because that is in the 3rd row, and we're telling it only call on rows 1 and 2. So here in bold, I've emphasized the fact that what you're actually doing is you're identifying both conditions have to be true in order for it to be displayed, or if you're going to be assigning a new variable to whatever elements you're calling on within that array. All right, so let me repeat that command just to make sure it works the way I have it on the screen. So if we say I want to have 1 through 2, meaning the rows, 1 through 2, and then columns 2 through 4, then it doesn't include column 1, and it doesn't include row 3. Just all of the other data is shown. All right. Everybody remembers how to transpose a matrix? Here's an animation that's showing how to transpose a matrix. If we start off with 1, 2, 3, 4, 5, 6, and so this is 3 rows, 2 columns, and when you transpose it, what you're doing is you're flipping it, so everything that was in a column is now in a row, and vice versa. So instead of having 3 rows, now we have 2 rows. So I think that animation kind of shows what transposing of a matrix is. And in Matlab, the apostrophe command is the way that you do the transpose. And so create A with the numbers that are shown here. This is a 3 by 2 when we first create it. And once you've created A, then have it transpose that matrix. And what if you double transpose the matrix? Well, it's just like flipping it back again. So it's the original if you double transpose the matrix. All right, so did everybody get A created? Okay, so we've got A is 1 and 2, 3 and 4, 5 and 6. So we've got A. And if we transpose A, then it flips it. And we could, now, one thing I want to make sure that you understand is that A is the same thing it always was. If I call on the variable A, it's still going to be 3 rows and 2 columns. So all we've done is we've said display right now the transposed version of A on the screen. If I wanted to save this new 2 by 3 matrix, I'd need to assign it a new variable. So I'd need to say something like C equals A apostrophe, and then that's going to be saved as a 2 by 3 because A is still 3 by 2. So remember that some of these operations are just showed on screen and it's not actually changing the matrix. All right. Did I skip over something here? Oh, okay. So, by the way, you don't actually even need the parentheses to create a matrix. So this one we've seen before. This is a 1 by 7. So if we wanted to have B be from -6 to +6 in increments of 2, it would create a 1 by 7. And then you can use the flip operation to create 7 rows in a single column as you're actually entering it in. Okay, so if we start off with B is -6 in increments of 2 to +6, okay, we've got that. But what if we wanted it to be, instead of a single row of data, if we wanted it all to be in a column? And sometimes we do. We need it to be in a column if we're going to be doing solutions of simultaneous equations, for example. So we could say -6 to 2 to 6, but we want it flipped so that its default is to put all of that data on a single row, but now make it in a column instead. And if we open up the B that we've just defined, then it's going to be 7 rows and 1 column, as we would need it. All right, so creating random numbers is one of the built-in functions that Matlab has. The thing that's strange about it is that today I had it generate 2 sets of random numbers that were identical. And I mean, that kind of like is contradictory to the whole definition of random, right? So try this. Create a variable that's y equals rand 4, 5, and I'm wondering if we all have different data or if we all have the same data for what it creates. So y equals rand, and we're going to do a 4 by 5. Okay, 4 by 5. Yeah, not very random, right? It just did here the same stuff that I've got in the presentation. Did everybody get it to create the same thing? You're saying no.
I did 3 of them all the same in one.
Well, but the first time you did it, did you get 8147 in position 1-1? You didn't. Raise your hand if you did. Most of us did. That's not very random. I don't know. I hope that it has a better random number generator than that. There's a lot about programming I don't understand, but especially in encryption, it's really important to have effective random number generation. Otherwise, your encryption can be cracked like no problem at all. But if we do it again, if we have y equals rand 4, 5, it'll give us a different set, I think, a different set of numbers. But again, I'm wondering, do we all have the same numbers? So did you get 0.6557? Bizarre. It must be, it has an order of random numbers that it generates. Like, I don't know, this is the first random number that I'll generate. This is the second random number I'll generate. It's going through a list somehow. What it does is it's going from 0 to 1. All of those random numbers are within that. I'm going to put air quotes here. All of those random numbers are within that domain. Well, at least now you know that function exists. How good it is an open question. We can also put in, we can replace individual values that are inside of our matrix. And so let's see, here's our y, our so-called random numbers, and we can reassign values. So within y, I want row 2, column 2 to be replaced with the number 4. Right now it is, row 2, column 2 is this 0.7577. Since I did my random another time, it's not the same as what's shown here. But if I reassign that number, oops, okay, okay, here. Yeah, all right, so it overwrote it. And if I want y, the first row and the first column to be equal to pi, then it overwrites its previous value now with whatever number I choose to insert. So that's how we can change things up at the command line rather than opening up the individual variable. So why would you want to do it in a command line way? If you're writing a script, you're not going to want to have to stop in the middle of the script and double click on the variable and find the spot and change the value. If you're going to be doing some operation hundreds or thousands of times, then it is faster to type it in on a line rather than use the graphical user interface to make the change yourself. Sometimes it seems like the graphical user interface is quicker than typing something in, but if you have to repeat an operation many times, then typing will save you over the long run. We can replace an entire row, not just individual elements within the matrix. So what this is saying is we want to replace the first 3 terms in row 3 with values 3, 8, and 11. So it's saying in increments of 3, go 5 plus 3 will give us 8, and then 11. So that's going to say the first 3 terms in row 3. So row 3, and then for the columns, we're saying columns 1 through 3. Okay, so if we try that, we want to replace in row 3 columns 1 through 3 with 5 through 11 in increments of 3. Yep. Okay, so now 5, 8, 11, it's been overwritten. Or you can replace an entire column or portions of columns. So here, this is saying all of the columns, all of the rows, column 4. And then what to replace it with is from 2 to 8 in increments of 2. And then the apostrophe there is because if it wasn't, remember, it would be in a row. And so anytime we want something to, a matrix to be a single column or transpose, then we have to use the apostrophe function. So let's try that. We're going to replace, here's column 1, column 2, column 3, here's column 4. We want to replace column 4 with some data, so we're saying all of the rows in column 4 we want to replace with starting at 2, going at increments of 2 through the number 8. And then the apostrophe there is because we have to replace the numbers. What we've already told it is we're going to be replacing all of these numbers, and so we have to replace it with 4 items that exist as a column. And so if we shaped it in any other way, then we'd get an error. So now we've replaced it. So if we didn't have that apostrophe there, let's see what kind of an error message it would give. If we said 2 to 8, yeah, oh well, I typed it wrong for one thing. So let me replace that. So let me, all right, there. But I think I'll still get an error message because what we've got now is we're trying to replace a column of data with a row, something that is row shaped. Oh, well, it worked. I wonder how it interpreted that. Let's see. It replaced, did it do anything? It did nothing. Oh, all right. So it didn't give me an error message, but it didn't do anything because the array y is the same as it was before. Okay. So if you actually want to replace it, then that apostrophe has to be there. It can give you statistics about your matrix. If you want to know the length of the matrix, then that'll tell you the number of elements, so the size. Let's try these out. We've got right now A. Let's see, what is A? I have caps lock on. Oh, maybe I've got capital A, but that's it. All right, so length of A. So a length of 3. I'm real surprised it's telling me it's got 3 elements. Let me try that with y. Length of y. 5. Yeah, I guess I don't understand what length means because I don't see anything about this that is 5. Let's try the size of y. That's a 4 by 5. That I can tell you. It's meaning that there's 4 rows and 5 columns. So I guess maybe length is saying it's the number of columns. All right. And we can do functions like mean, for example, but it'll do it for an entire column. So if we wanted to find out the average, here's our matrix y. If we wanted to know the average of every column, then we can do the function mean of y. And so what it's doing is it's finding the average of each column and providing it as a single row. So the average of 2, 4, 6, and 8, the average of that is 5, and so on. All right, so here we are. Finally, we've just been sort of talking in hypotheticals till now. This is where we actually get to do some real work with 2D arrays. So let's say we have a system of equations. 3 equations, 3 unknowns. You know, there is a solution for x, y, and z inside of this system of equations. And we want to know what is x, what is the value of y, and what is the value of z that will make all 3 of these equations equal on the left side and equal on the right side. So we wanted to solve for those. Well, you may remember that you set up a solution like this. First of all, you create a 3 by 3 matrix that has the coefficients in front of the variables x, y, and z. And then on the right-hand side of the equation there, we've got the numbers that were on the right-hand side of our systems of equation. And the approach for solving for x, y, and z is that you take the inverse of this matrix and multiply it by what's on the right-hand side of the equality. And so that is the operation that we're actually going to do in Matlab to find out what is x, what is y, and what is z. So the first thing we need to do is create the matrix that represents the left-hand side of the equation and the vector, meaning just the single column of data that is the values on the right-hand side. So let's create those as shown. Okay, so we're going to have A, and B, let's just double check that they're as expected. Here's our matrix A. It looks good. And our matrix B. Oh, I did it wrong. See, B needs to have the prime there, the apostrophe afterwards, because right now I've created just as a single row. So let me do B over again. It should be 1.2, 0.6, and 0. And then that apostrophe should be there to make it clear that it's going to be a column of data. So let me check on B again. I'm glad I checked. By the way, you could also have created B this way. Since it's in even spacing, you know, it's going 1.2, 0.6, and 0. There's a pattern there. I don't think it'd end up saving you any keystrokes in this case, but you know, you could have said go from 1.2 to 0 in increments of 0.6, and that would be another way of creating B. So anyways, we've got our matrix and our vector, and so here is the approach, remember, that we would want to use to solve this system of equations. We want to multiply the inverse of the matrix by the vector. Now there's a couple of ways we can do it, and we're going to get the same answer with all the different approaches. So you could use the inverse command. So that will solve for the system of equations. Let's try that. Let's try x equals the inverse of A times B, and find out what we get for x. All right, good. And so what that means is if we go back to the original equation, this is the one we're trying to solve here. If we substitute in 2.1923 into x, and 2.0538 into y, and 1.8 into z, combine it together as shown, then it'll be equal to 1.2. And so for each one of these three equations, x, y, and z. Now, it's a little bit confusing that I've called our solution x. Maybe we should have assigned that a different variable, because the first number is what in our matrix we were assigning the variable x. The computer doesn't know that in our equation that unknown was being called x. It just knows that it's the first variable in the matrix that it's solving for. So don't be thrown off by this saying x equals. I mean, it's the first row in the array that is the solution for x. The second row is the solution for y, and here's the solution for z. It's just we happen to assign that, that vector the variable x. We could have called it anything else. Okay, so that was one way to do it with the inverse function. We could also say x is a to the power of -1 times b. Okay, we get the same answer. And we could say x is equal to a, and now this isn't the normal division. Sorry. X equals a left division b. We get the same answer. So that's not the normal divided by symbol that we do. It's left division, and that's how we would, that's the key we use for arrays. So the answer is the same, but believe it or not, it took a different amount of time to do each one of those. Did you notice that the bottom one was faster than the rest? Did you notice? They all executed pretty quickly because, you know, computers are fast, and also because these are small, it's a small system of equations that it's solving for. But if you have a really big array that you're trying to do some math to, then there can be differences here that actually add up and make a difference. So Matlab is very versatile. You know, we just showed 3 different ways to solve the system of equations, but we engineers love to be efficient. That's what we're always aiming for, is creating the solution that costs the least amount of money, that uses the lowest number of resources, that's the fastest, and so on. And in programming, the same thing is true. We have to find methods that are quickest for solving things. And so it's kind of interesting. Matlab gives you a tool to assess how quickly your scripts are running, so that you can know whether one program gets to the answer faster than another one. So it's the fastest choice that is the best when you have multiple ways of doing something. I guess maybe we should say the best way is the one that you're going to make the fewest number of mistakes on. You know, if you happen to understand one method and it's comfortable for you, then, you know, use that method, because you make one mistake and you're going to have way more wasted time than a couple of cycles on a CPU. But all other things being equal, go with what's fastest. And so the way you can test a script to find out how long it actually took to execute, there's a command called tick and then another command called talk. And you can embed those into a script, and what it tells Matlab is start measuring the time and then stop measuring the time. And then when the talk is finished, it'll tell you how long it took. So you put in a pair of tick-tock, and then whatever's in between the two, it's going to be measuring the amount of time it took to execute. Now, you didn't notice that there was any difference in how long it took to take for that simple 3x3 matrix that we were working with before. But let's say, what if you had a 10,000 by 10,000 system? Then it's going to make a difference. So let's try that out. Let's create a script that creates a 10,000 by 10,000 size matrix, and that's A. And then B is going to be 10,000 rows, but just a single column, and it's filling it in all with random numbers. And then we're going to do a tick-tock And in here, we're going to assign x1 to be the inverse of matrix A times B. So it's just multiplying the matrix, not solving for a system of equations. And then our next tick-tock is going to be the other method, where you're taking matrix A to the -1 power. And then the third method that we used previously, which is A left/B. Now don't type this in at the command line. It won't work if you type it in at the command line. We need this to be a script. Because if you type it in at the command line, you type tick and the clock is starting after you press enter. And so you're measuring your own reflexes and typing speed rather than how long the computer is taking to execute something. So if you don't remember how to do a script, what we want is this button here, new script. And it'll open up this editor for us. And let me scroll over so that you can see that. So here's what we want to copy in. All right, we're going to clear the screen, CLC. A is the random 10,000 by 10,000 matrix. And be sure to suppress the echo. If you don't suppress the echo, your screen will just be filled with random numbers for a long time. Okay? And then we're going to create another vector, which is 10,000 rows, but only a single column. All right, and then we're going to start our first tick, which is like begin the stopwatch. And now once the stopwatch is started, we want x1, some new variable, to be the inverse of A times B. So we're just doing that to find out how quickly it can take the inverse of the matrix, really. That's going to be the majority of the time that it's taking. And then tock means time is finished and tell me how much it took during the elapsed tick-tock cycle. And then we'll start another tick. Now this is going to take a few minutes actually for it to calculate, especially if you have like Octave installed on a netbook, you know, like a really weak laptop. I got a laptop on Black Friday, a Dell, cost $99 for the whole laptop. It runs really, really slow, but it was $99, so I don't care that much. It's the kind of laptop that if you dropped it or spilled coffee on it, you'd kind of just shrug your shoulders and buy another one. All right, so save that script just so you have it as a reference. Oh, Microsoft OneDrive. When will it ever learn that nobody cares? All right, so I'm going to call this one tick-tock and save it. Hopefully there's no mistakes in there. Let's see what it'll do. I'm going to run it, and I think I'll get a command about changing the folder to the path that I've saved my M file in. All right. So nothing's happening, right? Down here it says busy. So the calculations are ongoing. And we wait. Oh, I've got an error. Let's see, what did I do wrong? Oh, I think I put in one too many zeros on mine. All right, there we go. 10,000. I pressed, all right, so I'm going to save that again. Run it. All right, it's busy. It's working. Now, part of the time is creating the matrix, but we didn't start the tick-tock until after the matrix is created. So some of what we're waiting on right now is just it filling in all those random numbers. The first one it did in 16 seconds. That's faster than I did it on the MU remote server today, and it took about 35 seconds for the first one. Is my computer faster than yours? Or did you guys take about 16.8? 18? 17? I must have a little bit more RAM in this instructor station. How much? 16.4. You've got a real fast computer there. It's a screamer. I guess on your computers the CPU is built into the monitor, right? Maybe it has something to do with that. All right, so which method is the fastest? It's A left/B is the fastest because it only took 6.3 seconds to execute. Pretty quick, right? I guess. By comparison, these times are from Microsoft Surface Pro. And so it's another one of those, it's basically a tablet that's running Microsoft Office, and it's running off of a battery and doesn't have big fans to cool it off, so it's not going to be running as quickly as a larger desktop might. Yes? I'm sorry. Let's see if we can. It's just going to be a programming mistake. That's the only option. Let's see. Random 10,000 by 10,000, yes. All right. Too many arguments. Tick tock, tick tock, tick tock. Now, just point of order. I don't think that space can be there in the name. I don't know that that might be it. So why don't you save as a different, just like tick tock without the space. Yeah. Let's see if now you could run that. Now, is it running longer than it did before?
It didn't run at all before.
All right. I bet it was just the name.
Yeah.
All right. Remember, Matlab is real picky on what you name your M files. You can use an underscore, but not a hyphen. I don't know if you can start with a number. It doesn't like variable names to start with numbers, so it may not let you do that. Spaces, it doesn't like a space in the file name. So we all got our tick-tock done to calculate, I hope. Okay, now matrix algebra, we have to use that dot operator. Like we were talking about before, you can't just do the multiply symbol. You have to do dot multiply for a matrix. The same with divide or power operations. So if we have our good old matrix X, we want to square that. So each one of the elements inside the matrix is going to be squared if we do X dot to the power of 2. Okay. So here is X. Oh, I've reassigned X since then. Well, let me get X back the way that I want it to be. X is okay. 5, 35, 43, 7, 4, 76, 81, 8, 21, 32, 40, and 3. Okay. Won't suppress the echo because I want to double check that I typed everything right. Seems fine. Okay, so if we do X, we want to square each element in the matrix. We do X dot squared. And here it gives me 25, which is 5 times 5, 16, which is 4 times 4, and so on. Okay. If you have a square matrix, this is just to demonstrate. So let's say this is C. If you say C squared, it's not going to give you an error message. What it should have been, like if we wanted to multiply each element in the matrix by itself, the command that we should do is C dot to the power of 2. And so then that would give us 1 times 1 is 1, 4 times 4 is 16, 7 times 7 is 49, and so on. But if we accidentally forgot the dot, this is what it would give us. Just for a square matrix though, because what it's doing if you say squared on an already square matrix is, you may remember that matrix multiplication where, for example, you're multiplying each row by another column, and so for example, this 30 comes from 1 times 1 plus 2 times 4 and 3 times 7, all added together. So there's 21 plus 8 plus 1 is 30. So it's doing some calculations if you square a square matrix, but it's matrix multiplication. And so just a word of warning about that. If you forget the dot operator, sometimes it's not going to give you an error message when you'd be better off having one if what you really want to do was multiplication of the individual elements. So extending along those same lines, if we have this as matrix A and this is matrix B, then multiplying the two together is going to be multiplying the 1 times 9, 2 times 8, 3 times 7 would give us the 46, and then 4 times 9, 5 times 8, 6 times 7 would give us the 118. Okay? That's matrix multiplication. And if that's your intention, if you want to multiply those two matrices together, you have to make sure that everything's the right size. And so if we had 4 columns in A, then we couldn't multiply A and B together, because you notice that B only has 3 rows. And so it would need a 4th row if there were 4 columns in A. So the right size has to exist in order to be able to successfully multiply them together. All right. That's it for today. Now, I said that we might have some time to work on, or you would have some time to work on the homework assignment. So we've got, class is scheduled for another 15 minutes. You're free to leave now if you'd like, but you can also stick around. And what I'm going to do is I'm going to open up the lecture to where we were talking about polyval and polyfit, just to sort of review some of those concepts. And it won't be a formal lecture or anything, but I'm going to work through a couple of illustrations that showed polyval and polyfit. So before you go, just a reminder that the assignment is due before class on Tuesday. So that's it. I'll see you then.